Hello, my name is Mason Cipollini, joined by my lab partners Colin Brown and Leif. This is Lab 3.
In this lab, our goal is to evaluate the beam profile of a laser after it passes through a beam expander. To understand how the beam expander works, consider this simple illustration. On the left is the objective lens, and on the right is the collimation lens. The expander operates by placing these two lenses in a confocal configuration. This means the distance between the objective lens back surface and the collimation lens's front surface equals the sum of the objective back focal length and the collimation front focal length. With the lenses arranged this way, collimated input light is converted into a magnified, still collimated output beam. To understand how a beam expander magnifies a beam, it helps to use similar triangles. In the illustration, two right triangles are outlined in red, each sharing the angles alpha and beta. Because the triangles are similar, each dimension in one triangle scales linearly by the same factor to match the other. Because every dimension of a similar triangle is scaled linearly by the same parameter, we can quantify that parameter, in this case as the ratio of the focal length of the collimation lens and the focal length of the objective lens. The object and image, both outlined in yellow, are linearly related by this magnification constant. Armed with knowledge of how a beam expander works, we can now proceed. For our experiment, we required a beam expander that could provide at least 10x beam expansion ratio. We chose a 16.5mm focal length microscope objective lens as our first element in the beam expander, meaning we would need a collimation lens with at least 165mm focal length. For this setup, we had two collimation lenses available, 200mm and 300mm. To compare directly with our previous experiment without a beam expander, we reused the 200mm lens, leaving the 300mm lens for the beam expander. This gives an expansion ratio of 18.18. The laser's initial beam waist was measured at 394 microns, which expands to 7.16mm after the expander. To capture at least 99% of the beam power, we use the rule that 99% of the power lies within 1.5 times the beam radius. This yields a minimum required collimation lens aperture of 21.49mm, which our lens comfortably exceeds. Lastly, to ensure beam quality, we placed a spatial filter at the intermediate focus between the objective and collimating lenses, sized to pass about 99% of the laser power. Our pre-lab calculations gave an optimal pinhole diameter of about 27 microns. Since a 25 micron filter was unavailable, we used the next available size, 50 microns.
Before assembly, each component required alignment. We first aligned the laser by adjusting for near and far views with a pinhole along the rail. X and Y translations would be adjusted at the near, and the tip and tilt would be adjusted at the far until the beam traveled cleanly through both ends. The collimating lens, placed on translation stage, would then be aligned along the optic axis. Adjusting the tip and tilts of the lens mount would send a retroreflection from the flat surface into the laser cavity. Similar adjustments to the X and Y translation would send the reflection from the convex surface into the cavity. Next, the microscope objective attached to the spatial filter stand would be aligned with the laser by adjusting X and Y translations using the post and translation stage until the output beam was centered upon a reference surface. Once this is aligned, the chosen spatial filter would be added in front of the objective on the stage. Adjustments to the filter's X and Y positions would first be made until the beam came through at the fullest visible intensity. Then, the Z position of the objective would be adjusted arbitrarily, where the filter would need to be adjusted again. The two adjustments would cycle until the fringes of the output are no longer visible on the surface, leaving only a solid, intense beam. With all components individually aligned, our 300mm collimation lens is placed back onto the rail after the spatial filter. This lens would be then translated along the optic axis until the beam roughly maintains the same diameter at both near and far distances, collimating that beam. In our assembly, the addition of the lens showed apparent misalignment of the spatial filter stand, requiring us to realign both the objective and filter. Once realigned, we were able to properly collimate the beam using a pinhole method similar to the laser alignment.
With the lenses of the beam expander assembled and aligned, the collimation can be tested using two different shear plates. The images shown from left to right are undercollimation, ideal collimation, and overcollimation, with the position adjusted to reach approximately 45-degree fringes. When the beam is undercollimated, the fringes tilt clockwise away from the reference line, and when overcollimated they tilt counterclockwise. By the Z translation required to achieve 45-degree fringes, we can see the 2-inch shear plate is far more sensitive than the 1-inch plate due to a narrower wedge angle in the shear plate. To determine the amount of power through the expander, power readings were taken at 4 locations using the photodiode, direct from the laser, after the microscope objective, after the spatial filter, and after the collimation and focusing lens. We found a 12.9% loss through the microscope objective and an 8.8% loss through the spatial filter. The loss in the spatial filter is likely due to a slight misalignment along the z-axis, as the beam quality was very smooth and symmetric, suggesting X and Y translation was not interfering with the beam. Finally, the beam can be profiled using the same procedure as in Lab 2, with the E1 position in front of the beam waist and E2 behind the beam waist. At each position, a knife edge is inserted and its position recorded using the optical rail. We chose an E1 of 43 mm in front of the beam waist and an E2 of 40 mm behind the beam waist. Then, the photodiode is inserted and the knife edge is scanned across the beam in the X direction in 50 micron increments. Shown in the second diagram is the setup of profiling the beam at E1. Finally, the beam diameter at each location is calculated as the difference in knife edge position at 84% and 16% normalized intensity. Here we have our beam profile curves at E1 and E2 overlaid with the theoretical value from the calculated beam waist and profiling equations. We see a strong agreement with the theoretical values of our obtained beam wastes of 1.58 mm and 1.22 mm at E1 and E2 respectively. Finally, we can calculate the new beam waste using the equations from the previous lab, obtaining a beam waste of 5.97 micron and a Rayleigh range of 0.177 mm. This is reduced by a factor of 16.4 compared to the previous lab's beam waste diameter, successfully creating a spot more than 10 times smaller. This also agrees fairly well with the beam expansion ratio calculated from our beam expander radii, where we expect them to equate.